the very first variant of scheduling is what we can call minimum latency resource unconstrained scheduling. So, my goal is simply minimize the latency that is required over here, but do not worry about the number of resources that you are going to use. We have already seen how to solve that and we had a name for it. What is that? What is the name for that type of scheduling? ASAP. Okay. So, ASAP scheduling does exactly this. Its goal is minimize the latency, do not worry about resource constraints. Okay. So, what would an ASAP schedule for this look like? It's pretty much what I have got over here, right. So, this also corresponds to the ASAP schedule. The second variant of it is so called latency constrained resource unconstrained schedule, right. So, what I am saying in other words is the maximum latency where I need to stop is given, but there is no limit on the number of resources that I can use. Okay. This has many different solutions. If I look at it, ASAP itself is already solving this problem, right. It has a latency constraint. As long as, unless my latency constraint is greater than my critical path, I anyway cannot solve this. So, this can only be solved if latency constraint is greater than my critical path, greater than or equal to the critical path of my existing graph, right. So, over here for example, what is the critical path length? 4, right. Again, I am going to make the simplifying assumption that I am talking about the unit delay model. Here clearly it is not the homogeneous processor model, but it is the unit delay model that I am going to assume. And if I assume unit delay model, it means that every task over here takes one time unit. The critical path is essentially along 1, 3, 4, 5 or 2, 3, 4, 5 and takes 4 time units. So, the minimum latency constraint that I can give is 4 time units, because if I say you have to schedule it within 3 time units, it is fundamentally not possible for this graph, I can't do it. Okay, but as long as I say 4 or anything greater than 4, I can do it. And like I said, this has multiple solutions. Both ASAP and ALAP are valid solutions to this problem, along with a whole bunch of others where I do not necessarily schedule a task as early or as late as possible. As long as it does not violate any constraints, it is a valid schedule. Now, why are these two important? Because ASAP is something that can actually be obtained in polynomial time. Okay. How do I go about doing it? If I go back and look at this graph that I have over here, right, all that I need to do is basically look at the nodes in some kind of order. What order is that? From the one that is basically the one that needs to, I essentially look at the critical path, find the ones that are earliest in that critical path and then basically go further down from them all the way down to the last task. Okay. So, that ordering is all that I really need to take care of as far as the any one of these schedules is concerned, right. Can I build that order systematically for a graph? It turns out yes, there is an algorithm called topological sorting, which basically allows you to find an ordering of these nodes such that none of these dependencies are violated, right, and I can just basically pull out the nodes in that sequence and schedule them as early as possible, as and when they become ready. Okay. So, this problem, these two in other words, are both solvable in polynomial time. But supposing I now put a resource constraint. So, let me go back, look at this same diagram over here and say what happens if I put a constraint saying that you are only allowed to run 2 multiplications at any given point in time. Anyway, the multiplications get over in 1 clock cycle, so I am not worried about pipelining or any such thing, but I can only run 2 multiplications at a point in time. and a maximum of 1 addition, 1 ALU operation. Okay. So, under that constraint, how would this look? In other words, what I am doing is I am bringing in the concept of a resource constraint, 2 multipliers, 1 adder. Under this constraint, what kind of schedule can I come up with? How would I go about doing the scheduling? Let me just redraw that diagram over here. How would you make use of this and do a resource constraint scheduling? Can you give me an example of how you would go about trying this out and what can you see as the result? Which operation would you schedule first? Right. So, what I have basically is I have time 0, 1, 2, 3, etc. And I have, I will call them M1, M2 and A. So, there are 2 multipliers and an adder. Okay. And what I am asking you is at each time instant, what should go on M1, what should go on M2 and what should go on A. Okay. So, which one would you put on M1 and M2 in time 0? 1 and 2. Okay. Is there anything else that could also have gone on to M1 and M2? Yes, 6 and 8 could also have been scheduled, okay, but it looks as though it makes sense to do 1 and 2. Why? They are on the critical path. Okay. So, this what you have just done over here is an example of a heuristic approach. Okay. So, the word that we will be using is heuristic, right. A heuristic is essentially, it is an algorithm in the sense that it is a systematic procedure to solve a particular problem. The difference between this and our normal understanding of algorithms is that when we talk about algorithms, usually we are concerned with an algorithm that optimally solves a problem, that gives you the correct solution, right. Whereas, over here, as I have sort of hinted at without proving, and I am not going to try and prove, right, this problem is a hard problem. Algorithms that will solve it optimally are not going to work in a polynomial amount of time, they will usually require time exponential in the number of nodes that we have. Okay. Whereas, what we have just presented over here is a heuristic. It is an idea that basically makes sense, that seems like it should work in practice, that should give us good results. But if you try to prove that, as long as I take the nodes in the order given by the critical path and put them over there in the schedule, that will give me the best possible solution, you can't prove that. In fact, you can disprove it, you can come up with examples that will show that that won't work always in practice. Okay. So, this idea that we basically use the critical path as something to guide us, right, is a heuristic, and in this case let us just make use of that and go ahead with what we want over here. I am going to basically say operation 1 and 2 are going to be scheduled over here. What about on A? What can I schedule on the adder, on the ALU unit? Operation number 10. That is the only one that is free at this point anyway. Okay. Alright, what about at time instant 1? Now, what should you run? Okay. Should I run 6 and 8? Because those were the other ones that were right on top and were free, or should I run 3? Right. So, all 3 of them are now free. 7 is still not available, in the sense that 7 still requires 6 to be executed before I can start it, right. But all the other 3, 6 and 8, all the multiplication operations are available, and which choice I make over here is actually crucial. Okay. If I decide to put 6 and 8, then 3 has to get pushed down to an even later time instant. Okay. Is that necessarily a bad thing? It is not entirely clear, it is not as obvious as it looks to start with, because you have other constraints also at play over here. Okay. But in any case, at least to start with, what I am going to do is straight away put down 3 and 6, right? And on the ALU, what can I do? Again, the only one that's available is 11, so let me go ahead and execute 11. Okay. At time instant 2, now the other two multiplications, 7 and 8, are both ready. I can execute both of them. The problem is, and okay, so at this point I can also now run on the adder, on the ALU unit. What do I do? Operation number 4. Okay. At time instant 3, there are no multiplications left. Okay. What should I execute? I have two choices, 5 or 9. Does it make a difference which one I execute? No. Okay. And again at time instant 4, I have this, so I basically finish up with 9. Okay. So now you can see a couple of things. One is the resource constrained schedule, we were able to create it quite easily, right? Is there any way that you can prove that this is optimal for the given resource constraints? Could I have done anything better? So my resource constraints are 2 multipliers, 1 ALU unit. Is there any way I could have done better than this? There are 5 ALU operations, so fundamentally I cannot do better than this. Okay. So as long as I meet that constraint, 5 ALU operations in 5 clock cycles, it means that the ALU is now running at 100% hardware utilization efficiency, right? There are 2 multipliers which are not at 100%, they are only at 60%, right, because only 3 out of the 5 clock cycles are actually occupied. Could I have reduced that and made it 1 multiplier? What would have happened then? I would have had to push to 6 clock cycles. Okay. So this already shows you an interesting sort of trade-off over there, right? If I reduce the multipliers from 2 to 1, right, automatically it would have pushed it to 6 clock cycles, but then possibly I might have got a schedule where the multipliers could be running at 100% utilization. The adders then definitely will not be, because there are only, or rather the ALU will definitely not be, because the ALU is only capable of doing or only has 5 operations on it. But more importantly, if you think about it, what you will see is that even that may not work out completely in practice, because there are other dependencies. So unless you are able to finish the ALU operations and then the multiplication operations and then push the ALU operations correspondingly immediately after that, you may not be able to hit 6 cycles latency also. Okay. Just for an example, I am going to consider another variant of this, the same 2 multiplier 1 adder resource constraint, right. So in this case we will still stick with 1 and 2 over here and 10, but now what I am going to do is do 3 and 8 instead of 3 and 6. Okay. And what happens as a result of that is, in cycle number 2 I can only do 6, I can't do anything else, right. Well, I can still run 4 over here. Now I can only do 7 over here, right, and I could do 9 at this point. Now I have finally completed what I require over here, and yeah, 5. So this is another variant where I am still able to meet the timing constraint, right. It's a coincidence. It turns out that we were lucky that we were able to meet this timing constraint, but you can see that this has, for example, got pushed into 2 different steps over here, right. In general, there could be something else that creates a gap that I simply cannot take care of and fill. Okay. So you can see from this that whatever we have done over here, there were multiple choices that were available to us. Which one should I have picked at any given point in time is not very clear upfront, right. The choice saying that I will pick the one that is on the critical path and try to schedule it early is a heuristic. I am not going to prove it in class. It can be shown that no systematic choice that I have over here can give me an optimal solution as long as that choice was essentially based on some kind of a polynomial time cost computation. Okay. There is of course the possibility that I actually go through all the possible options and then say, okay, pick this one, it is the best, but that is not a polynomial time algorithm. Okay. So, this is a heuristic. The fact that we have a resource constraint still allows us to come up with this schedule, right, and this particular approach that we have done is essentially a form of something that is known in general as a list scheduling problem. Okay. So, what we are doing in list scheduling is we are maintaining lists of what are the actors or nodes that are ready to execute, ordering them according to some priority, and then deciding at any given point in time which of them is going to execute.